Hey guys, how's it going? So I want to make sure this sounds okay. I'm starting the live stream a couple minutes early. If you guys can comment in chat, can you hear me okay? Is the mic coming through all right? And my computer screen's down here, so I'm looking down there to see what you say in the chat. Yeah, waiting to see. Anybody, can you guys hear me? Is it okay? Anybody can comment. I don't see any comments going on the live chat. Okay, cool. Prana, thank you so much. All right, so you can hear me great. We're about to get started here. This is my first ever live stream. I'm a little bit nervous. I mean, I've done a live stream, but not a lecture on live stream. So I'm a little bit nervous right now. I've taken a lot of caffeine. In addition, yeah, let's just kind of get started, I guess. So this is my lecture in conjunction with the start of the Phi-MC math competition. It is going on this weekend. This lecture is not specifically for them, although they were invited to attend. I'm sure that somebody in the comments can explain to you exactly what that competition is and what grade levels are participating. But this lecture is specifically towards anybody 13 years of age or older. And so it's that's what we're doing here. Now, I call this block pathing, right? And the idea is if you're starting at A and going to B, how many different paths can get you there? But before we get to that, this is not the official name. That's why it's got quotations. It's my pet name. It's what I call it. Most people would say counting paths on a grid or something like that. But I like to call it block pathing because I get to do that. Next up is combinatorics. What is combinatorics? Well, a long time ago, mathematicians were doing their mathy things, they're counting stuff, and people asked, oh, what are you working on? And they would say, oh, I'm counting. And they weren't that impressed. I mean, counting is 1-2 syllables, counting. Didn't sound too highly intellectual or difficult, and so mathematicians were concerned about this. And they thought, people need to appreciate what we're doing. We need a new word that's going to sound, multiple syllables and highly difficult. And so they came up with this word, combinatorics. And it's got 5 combinatorics. Yeah, 5 syllables. It sounds super smart, right? And so now when somebody would ask, what are you working on? Oh, I'm practicing my combinatorics. Oh. And people were stunned and impressed with their ability levels and their intellect. And so this became a popular word mostly for that reason. I'm just making that up. This is my version of how the word combinatorics came into being. I have no idea the exact, history behind its development. Maybe you want to look that up and leave it in the comments. So combinatorics is really just a fancy thing for counting. That's basically it. And so we're going to get into that in a moment. One quick note about competition math in general. In competition math, it's going to be important for you to kind of think about why did the test maker or the item writer, right, they're writing a question, why did they include such and such information? Why are they telling me this? The best problem solvers are constantly asking while they're reading a question, why did they tell me this? What does this mean? And then they try to process that as they work through the problem. And kind of in line of that thinking, I'm going to start with a topic not quite directly related to this, well, yet, and we will see how it ties in. It's based on a 12th century mathematician from Italy. Now, Italy's pretty important, mostly because they gave us pizza. And I think pizza's wonderful. And if you're lactose intolerant or can't have cheese, I feel bad for you. Anyhow, I like pizza a lot. And so this mathematician's name is Fibonacci. And you spell that like this. And he made this whole sequence kind of famous. It's what he's most well known for. I don't know if he fully invented it or if he just expanded upon ideas of that time. Again, look it up in the history and find out. But the sequence is named after him. And let's kind of see how it works. Let's say that you have a pair of rabbits. We will call it a lowercase r. A pair of rabbits. Keep it. This is not one rabbit. It's a pair of baby rabbits. And there's one male and one female. And let's say that they become adults 1 month later, 4 weeks, right? 1 month about. And so now they will be represented like this, right? This is the adult pair of rabbits. And let's just say that this adult pair of rabbits produces offspring. Okay, so they're going to have an offspring the next month. This is the first month. This is the second month. The next month, they will produce let's say they produce ideally a pair of rabbits. And so they would have the adult pair here. This is the baby pair, became an adult pair in the second month, and now they're going to produce offspring in the third month in the form of a baby pair of rabbits, one male and one female. Okay, then what happens? Well, this process is just going to continue. And let's say every month, the adult mature pair of rabbits produces another set of 2 offspring, one male and one female. And this one also matures to adulthood. So now you will have the previous adult producing an offspring of 1 pair of rabbits. The previous baby pair of rabbits becomes an adult like this. And then in the next month, you're going to have the adult pair again produce another pair of rabbits. However, the previous baby pair is now going to become an adult. Okay? And the previous adult pair is still going to be there, and they're also going to produce a baby pair of rabbits. Let's keep going, shall we? Okay, so then in the next month after that, you're going to have this adult pair produce offspring. And then the baby pair's going to become an adult, but not yet produce offspring. Then this adult pair is going to produce offspring. And then this adult pair does the same thing. And then this baby pair becomes an adult. It shouldn't be a comma yet. And it will look like this. And so this is how it kind of proceeds. We're going to stop here and let's kind of look at the properties of this sequence. The total number of pairs of rabbits is as follows. 1, 1, right? 1 pair, 2 pairs, because there's 2 R's, 3 pairs, 2 adults, 1 baby, 5 pairs, again, keep in mind they're pairs, 5 pairs, and then this one is 8, and then the next one will actually be 13. And I'm not going to keep writing them out. That's a lot of R's to write. But let's actually look at something else as well. Let's look at how the adult pairs, just the adult pairs now, just the capital R's, there's 1 here, right? We have 0 here, and we have 1 adult pair here, and 1 adult pair, we're ignoring the baby pairs, and we have an adult pair here, and we have an adult pair, 3 pairs here, right? There's 2 pairs in this one, 2 R's right here, 3 capital R's here, and now there's 5 capital R's. Wait a minute though, this looks an awful lot like this one. It just happens to have a 0 in front, but besides that, it's the same sequence. This is Fibonacci sequence, and it's found by adding the 2 previous terms and making them the next term. So 1 plus 2 would be 3, 2 plus 3 is 5, 5 plus 8 is 13, and on it goes. And it has fantastically interesting properties. Google is your friend. Well, mostly. I'm not going to get into that. But you can look up things on search engines. How about that? Search engines are your friend. Pick one that you like and look up what you can learn about Fibonacci sequence. And so this one here, though, is a Fibonacci sequence within a Fibonacci sequence. And furthermore, let's do it for the baby rabbits, shall we? The baby pairs starting here is going to be like this. And then here is going to be another baby pair. And then here is going to be 2 baby pairs, right? So let me write it as numbers instead. So you're going to have 1 and 1, and then 2 baby pairs here, and then 3 baby pairs here, and lo and behold, the baby pairs of rabbits also make baby pairs. And so there's another Fibonacci sequence within the larger Fibonacci sequence, right? And so as a result, you can see how this sequence works. Okay, that's it for now for that. We're going to return to that later, let's see. And for now, we're now going to start looking at this idea of block pathing, as I call it. And so let's take a look at the first example we're going to do. I have pre-written them to save time and erasing time. Let's say you're at A and you want to get to B, but you want to go as efficiently as possible, meaning that you can only go down or you can go to the right. That's it, only down or to the right. There's no circling around, right? We're not going in random directions. Only down and to the right. You will have to go either 3 different ways. You could go all the way down, right? You could go down, over, down, or you could go over, down, down. 3 paths. Okay, we could also think of it though as a selection of D's and R's. I'm going to have to go down twice and right once. We could think of it as, since I definitely have to go down twice for all of them, which path do I go right on? And you would notice that there's three choices to make. You can go right here, you can go right here, or you can go right here. And those three choices are the total number of ways that you can get from A to B. We could also think of it as the number of arrangements of these letters, right? Unique arrangements, distinguishable arrangements, okay? So I could do DDR, I could do DRD, I could do RDD. And again, you'll see three arrangements. Okay, well that's easy enough. Let's take a look at the next one. Well, for this one, we've got a few different things to do. We're going to have to go down twice and right 3 times. So now we're going to have 2 D's and 3 R's. Again, you can think of this as the number of arrangements of these letters. But it's going to get long if we have to list it. So we're going to want to come up with a faster plan. So we'll get back to this one in a moment. Let's do something else. What if we had said, how many ways are there to get to this point right here? And we said there was one way, right? There's no, you just go down, that's it. You cannot go like this. And how many ways could you get to this point? Now you're gonna go down twice, but that's not 2 ways. It's just one way. You can only go down twice. And to get to this point over here, you could only go right once. And we're going to put the number that corresponds with the number of ways to arrive at that point, right, at that vertice or vertex, how many ways you can get there. Then how many ways could you get right here? Just this point right here. You could go right and down, or you could go down and right. There would be 2 ways. And as we know, there's 3 ways to get here. Let's take an approach like that down here and see if we notice anything interesting. So if I start at A and I come down 1 to here, and 1 to here, and 1 to here, 1 to here, and 1 to here. I hope you guys can see. I try to make the camera zoomed in enough so it's not too hard to read these numbers. Okay, then how many ways to get right here? Well, this is the equivalent of this choice right here. There would be 2 ways to get there. And then if I went down to right here, it's kind of like this choice here. There would be 3 ways to arrive at that point. What about over to here? Well, I could go right, right, down, right, or down, right, right. And you would have 3 ways to get there. What about over to here? Again, you'd be essentially choosing where to go down. 1, 2, 3, 4 choices about where to go down. And this would have 4 ways to arrive at it. Okay, but now it's starting to get kind of bigger numbers. It's taking more time. I really don't want to count paths. Maybe we can find something. We'll do one more like this and then look for a shortcut. What if I go down, down, right, right? That's one way. I could go down, right, That's downright good. All right, anyways, then you could also go down, right, down. So far we've got 3 ways. Then I could go over, down, right. That's a 4th way. I could go over, down. That's a 5th way. I could go over, down, right? The total there's going to be 6 ways. I'm not sure I counted those right because I'm used to doing it on paper. But there's going to be 6 ways to arrive here, okay? And so from that, you have a 6. But let's look at these numbers more closely. What is 1 plus 2? Well, it's easy. It's 3. And what is 3 plus 1? Well, that's 4. And this number is a 6, and these are 2 3s. Maybe there's a connection here. Maybe the sum of these corner numbers is this one. Now, why would that be? Well, it's simple. The only way to get to this spot is if you came from this spot or this spot. So if there's 3 ways to get here, and there's 3 ways to get here that are different ways, then those 2 are the ways that combine to make the number of ways to arrive at this point, and therefore the number of ways to get to B is 10, the sum of 6 and 4. Okay, so far so good. Let's advance it a little bit. Oh, before we do that, let's cover the letters one. How could we do these letters, the arrangements of these letters? Well, let's say there's 5 spaces, and you wanted to put these D's and R's in some kind of order. you'd basically be saying, out of these 5 spaces, I want to choose 2 of them to be D's. And you could say, well, I want this one and this one to be a D. Well, by default, the others would become R's. And so you would place the R's in those positions, and that would be one way. Keep in mind then, for every unique selection of where the D's go, that would be a unique way of doing it, okay? So we call that combinations, right? We're gonna say it's 5 spaces, and I want to choose 2 of them. Traditionally, it was written more like this, 5 choose 2. Sometimes it's written like this, the combination of 5 things taken 2 at a time. And then another way it gets written, which is my usual favorite, is like this. And it's the 5 choose 2. There's no fraction line here, although all the time I wrote a fraction line there when I didn't mean to when I was in school. So if you find yourself doing that, you're not alone. Okay, so what is combinations exactly? It's groups of things where the order doesn't matter. So for example, if I had A, B, C, D, and E, and I wanted to group any 2 of them, A and B would be a group, and A and C would be a group, but B and A would not be a different group. It's the same group as these 2. Specifically because it's the same 2 letters, we don't care what order they're in. Okay? So it's a group of things where the order doesn't matter. That's usually how it's used. Okay, so then how would we calculate combinations? Well, there's a simple formula. It's going to look like this, and I'm not going to fully develop the formula for you now, but it's going to use something called factorial, which is an exclamation point. Let's get rid of Fibonacci, well, his name at least. So you've got this symbol here. It's an exclamation point, but it means factorial. Factorial. And what is factorial? It's a really simple idea, actually. If I have 4 factorial, it's 4 times 3 times 2 times 1. It's the product of all the numbers starting at this one going down to 1. Further, 5 factorial would just be the same thing, but you can actually stop writing the numbers at any point and end it with factorial, because we know that this means 3 times 2 times 1. You don't have to write them all out. In fact, most people don't write the 1 because why? It's just times 1, right? So this is going to be n factorial, whatever this is, and then in the denominator, you're going to write the difference of these 2 in parentheses, n minus r factorial. And finally, you will take the bottom number and do r factorial. Simple, right? Kind of, maybe. Let's see how it works with this one. 5 choose 2 would be equal to 5 factorial, the difference, just subtract, 3 factorial, the bottom number copied next to it, 2 factorial. Now, to simplify this, you could write it all out like this style, or you could stop when you get to the factorial that's largest in the denominator. And you do that because, well, things cancel, and we like to save time because we're usually kind of lazy. And so we're going to put this here. 2 factorial is 2 times 1. We don't need to write that. We can just write 2. We can cancel the 3 factorials, and 20 over 2 is 10. And so this way, we can think of this as a selection of combinations. 5 choose 2. You're choosing 2 places to go down. Like I could go down here, and then over here, or something like that, right? You're going to go down twice. And then the R's, same thing. But wait a minute, what if we didn't focus on the D's? What if we focused on the R's? What if we said 5 choose 3 places to put the R's? Would we get something different? No, because if you calculate it with this formula, it's going to be the same thing. 5 factorial, the difference is 5 minus 3, that's 2 factorial, and then the 3 copied by itself is going to be 3 factorial, and these are identical. So whether you focused on the R's or you focused on the D's, you're going to get the same thing. Now, one last thing to point out about all of this, some of you might have learned the number of unique ways to write a sequence of letters, right? And the unique ways to write that, let's say you had a word like 11, okay? And you're gonna notice right away that there's 3 letter E's in the word 11. Did I spell it right? I think so, good. 6 letters, you would normally say if they were all different letters, it would just be 6 factorial. By the way, funny story, when I first started tutoring, there was a local high school where the teacher thought the kids couldn't understand factorial or something, and so she actually called it wow. So this was like 6 wow. Like, you know, like exclamation points in the English language mean something exciting has happened. And so she thought this would be a good way. Hey, it's not bad, but it's kind of amusing to me that we would call it wow. So sometimes I will call it that in my private sessions. It's 6 wow. Like sham wow. Okay, never mind. All right, so 6 factorial. And then what would you do? Keep in mind that these e's are not distinguishable. Okay, so let's say that they were. Let's say I could attach a 1, a 2, and a 3 here. And let's say I put them in a random order where it was like E2, E1, L, V, E3, and N. Now, what if I switch these two E's? I would have E1, E2, and then L, V, E3, and N. Now, we can tell these apart. These are called subscripts, by the way. It doesn't mean anything. It's just for notational purposes. We can tell these apart because of their subscripts. But if I took the subscripts away, you would not be able to tell them apart. They would look identical as far, well, maybe the writing would look slightly different because my handwriting is, but other than that, it would look the same exact arrangement, if you will. So what we have to do with this 6 factorial, because these are not really, they're not really able to be told apart, we have to divide by the number of ways that I could arrange the e's. Well, if you have 3 things, you can arrange them in 3 factorial ways, and so that's what you would have to divide by. You might recognize this is actually the same as 5 factorial. Why? Because 3 factorial is 6, and it starts with a 6, so I could have written it as 6 times 5 factorial over 6 and canceled to get 120. It's a good idea to memorize your factorials up until about 7 factorial, probably, about, yeah. Okay, so that's it. Why are we dividing by 3 factorial? It's the number of identifiable arrangements of the e's. And when we did 6 factorial, we didn't consider that they're not distinguishable. So to account for that, because we considered them unique in this calculation, we divide by the number of those arrangements of just the e's. Had there been another letter, like say 2 n's, then this would have become 7 factorial, and the 2 n's would also create another divisor of 2 factorial. Okay, so with that in mind, let's look at these d's and r's. Maybe you want to think of it as the number of words, quote unquote, words that you could create with 2 d's and 3 r's. Well, how many letters are there? Well, there's 5, so you would write 5 factorial. How many d's? There's 2 factorial. How many r's? There's 3. Doesn't this look familiar? It should. It's simply 5 choose 2 and also 5 choose 3. These are all related topics. All right, let's go to the next one. I'm going to first take away this C right here. I kind of wanted to have it be so you had to go through C to get there. But I want you to, well, now I guess we'll keep it. We'll keep it. I'll wait and show the other thing I was going to show later. Let's go to this one here now. And we're going to say that you're going to go from A to B, but you have to pass through C. How could we approach that? Well, we can just do the numbers thing if we wanted to. The numbers thing is kind of a basic level, like beginner's level understanding. It's usually done when you don't want to do combinations or you can't think of how to apply the combinations to the problem you're working on. But sometimes when it gets more complicated, it might just be the best way. Or there might be another way and you could tell me in the comments, but I usually use it on problems like this. Okay, so we'll get there in a minute though. If I had to go from A to C, we already know there's 3 ways to get to C, 1 and 1, and there's 2 ways to get here and 1 way to get here. And then if I wanted to go from C to B, I would now transfer these ways down to here, and keep in mind, you have to pass through C. This is not an option. So in this problem here, we have to pass through this vertex. Then how many ways are there to get right here? Don't think there's 4 or anything else or doubling this 3. The same 3 ways there were to arrive here are the same 3 ways that we could arrive here. Why? Well, you could go down, down, over, down. Or you could go down, over, down, down, or over, down, down, down. It's the same three ways. We didn't get new ways just because we went to a new node. Okay, well then, what about if I went this way? It's the same idea. You're going to have three like this. There's three ways to get to this point because you can only come from this point, and all three ways to get to here are the ones that transfer over, if you will. And furthermore, they will even transfer over to here as well. You can also think of it like this. There's 0 ways to get here in the context of our problem. So if I added 0 and 3, I get 3. And there's 0 ways to get here in the context of our problem. So if I added 0 and 3, I would get 3. If you want to put the zeros, feel free. Then you would take 3 and 3, you would add them, and you would get 6. And finally, 3 and 6 makes 9. So once we have that, that's going to be all there is to get there. But could we have done it with combinations faster? How many ways would there be to get here? Well, it is 3 choose 1. How many ways are there to get from C to B? It's again 3 choose 1. And why is that? Because you're choosing one path to go down. And if you multiply these, here's a hint, n choose 1 is just n. And you can think of it like this. If I've got, let's say, 5 pieces of candy and I tell you you can choose one and they're all different, how many choices can you make? Well, it's obviously 5. You have 5 choices of the piece of candy that you're going to take, right? You have 5 choices to make. So n choose 1 is just n, and 3 choose 1 is 3, and we multiply this to get 9. So once we become more advanced, we usually try to use a technique like this. 1 second, talking for a long time. The throat is dry. Okay, so next up, let's go to something where they've kind of forced our hand in going a certain path. We could go here and get to B, but we're forced to go through these points. But understand, it's just like the C. I could have, in fact, come over here and erased all of this and erased this block, and it would be kind of forcing you to go through this point. I could also come down here and go over here, but we can't take any of these paths, so we don't need to draw them. So how would I get to here? Again, it's 3 choose 1. So we would do 3 choose 1. How would I get from here to here? Well, now we've got 4 choices to make, right? You've got to go right twice. You've got to go down twice. You're going to have to do 4 choose 2 ways to get here. And so you would multiply by 4 choose 2. And then you would have to choose 3 ways to get here. You would multiply by 3 choose 1. Because we're filming this live, I'm not going to calculate this by hand, but feel free to practice at home how you would calculate this. This is 3 times 6 times 3. We should get 54. Let's check it out now. If I went one way here, one way here, one way here, 2 ways here, and 3 ways here, transfer the 3 along these paths. It would be 3 here and 3 here and 3 here and 3 here. 3 plus 3 is 6. 6 plus 3 is 9. 6 plus 3 is 9 again. This is 18. Transfer the 18 here, here, and here. It always transfers down and sideways, right? The same exact number that you arrived at are all the ways to get here and there. And then you will just add 18 and 18 to get 36, and we get 54. Which way was faster? It's up to you. If you feel bad at combinations and you don't want to do them, use the number path. The most important thing is that you get it correct. Over time, you want to work towards more efficiency. But if you're not quite ready for that efficiency yet, don't feel bad having to do this. I've done it on the AMC 10. It actually works just fine. I'm not going to do that problem today because it would take a while to set up, but it can be done that way. All right, last one for this type, and then we're going to show one more thing. You go from A to B, how many ways to get there? I'm just going to use the block pathing technique. It's pretty quick now. So 1, 1, 2, 1, 1, 1, 1, 1, 1, 1 plus 2 is 3, 1 plus 3 is 4, 4 plus 1 is 5. This 4 would transfer over to here, but not to here, because you're going to have ones from above. 5 plus 4 is 9. 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. This 4 would transfer to here though, because you cannot come here and over. Remember, you can only go down and right. So you would put the 4 here, you would add this 4 plus 5 to get 9. The 4 would also not transfer to here just yet, but instead this node and this node combine to go here. So you're going to be at 8. Then 9 and 8, you're going to have 17 ways to get here. 8 and 9, 17 ways to get here. And finally, 34 ways to get from A to B. All right, the last thing we're going to cover today, I'm actually just going to use this as an example, and we'll try to erase some of the numbers and the C and go through it as quickly as possible. Let's get rid of this space here, and we don't want that B. We've got this. Sorry for the erasing time. It is filmed live, and I don't really have the option of, pausing the video and refilming. So let's see what I wanted to show you. Okay, you're still going to have, wherever you start, you transfer ones across and down. All the nodes have one way to get to them. Let's keep going with this pathing technique. We've got 4 here, 3 here, 4 here, 3 and 3 is 6, 4 and 6 is 10, 6 and 4 is 10, 10 and 10 is 20. There's 20 ways to get to B. My question for you is, does these numbers look familiar? Some of you might know, in fact, those who are more experienced probably already know where I'm headed with this, but if you're of a lower level or introductory level to this kind of content, you might not be aware. So I'm going to give it away in the essence of time. Normally in a live class, I would have you think about it for a while, like in a class in session, with kids in front of me and stuff. But again, we're on YouTube Live, so I'm going to have to explain it quickly so there's not dead time. Let's do this right here. Hopefully I have enough space. Does anybody know what this is? Feel free to type it in the comments in the live chat. Or if it's probably already mentioned in the live chat when you watch this video later. I don't know if I'm going to have enough space to fit what I want to fit. And let's just erase this so I have the space to do what I want to do. This is going to be 1. This is called Pascal's triangle. But if you are from native mainland China, they call it, I believe, the Yanghui triangle. I could be mispronouncing that name, but that's what they call it there. That individual also did extensive work with this idea. And so Pascal's triangle, let's look at these numbers. 1, 1, 1. This would be 1, 1, 1. 1, 2, 1. 1, 2, 1. 1, 3, 3, 1. 1, 3, 3, 1. And then if I put a 1 down here, 1, 4, 6, 4, a 1 over here would complete this row. If you don't know what Pascal's triangle is, it's got a lot of ways to explain it. I'm not going to break it all down in this video. However, the simple thing to understand is you will add the 2 numbers here and they become this one. These 2 numbers will become this one. These 2 become this one. But wait a minute, if these numbers are really just combinations and they correspond with Pascal's triangle, wouldn't that mean that Pascal's triangle is just combinations? Yeah, actually, that's exactly what it is. We're going to erase here so I have some space to do something else in a moment. Pascal's triangle is just combinations. But this is not going to be 1, choose 1. We would actually usually call it 0, choose 0, where you have nothing, you choose nothing. Guess what? There's one way to choose nothing. And that's why this is a 1. This number here would correspond to 1, choose 0, and the other one next to it, 1, choose 1. I'm not going to write all of these. 2, choose 0, 2, choose 1, 2, choose 2. This is considered the first row below the top, 1. And so when you do this, it's the second row from the top. Even though it's technically the third row, you're going to have 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. The top number is the row number below the top row. Okay, so 1 row below the top, you use a 1. 2 rows below the top, you use a 2. 3 rows below the top, you're going to use a 3 for the n value, if you will. Pascal's triangle is just combinations then. In fact, when I was first learning combinations, it's quite common that if I knew this row and I needed, or this row even, 1, 4, 6, 4, 1, and I needed one of these, I might just write the row and calculate it instead of using the formula, right? Because this is 5, choose 2, the 10 that we saw earlier. Here's the 20 that we got down there, right? And so you're going to get, what is that? It's 6, choose 3. You're going to go right 3 and down 3. This is 6, choose 3. 0, 1, 2, choose 3. 6, choose 3. But the last thing that I want to show you guys today, what are we at so far in the feed? We're at 35 minutes. This is about to be done. The last thing that I want to show you guys is the following. Remember at the beginning when I said, in competition math, you always want to ask, why are they telling us about X? Whatever it is, whatever the thing is they want to tell us about. And at the beginning of this lecture, I talked about something called Fibonacci sequence. Go back and watch that part if you're watching the video later, because now we're going to see how it all ties in. If you were to look at Pascal's triangle and you were to draw slanted lines in a very specially drawn way, let's see what these numbers would look like. If I go through this one, I could put a sum of all the numbers on this line as 1. And if I was to go through this right here parallel to that line, I would again get 1. But if I went through these two, again, parallel to that line, you would get 2. And if I did it again, 1 plus 2 is 3. And if I did it again, 1 plus 3 plus 1 is 5. And if I did it again, 1 plus 4 plus 3 is 8, and this will go on to infinity. If you carefully draw the lines, you can make it work. 1, 5, 6, and 1 is 13, and as you can see, Pascal's triangle hidden within it has Fibonacci sequence. I'm not going to explain why that's there. In fact, if I ever learned it, I've probably forgotten what it is, but this is why search engines exist, and also math teachers with PhDs. Ask your local one, or whoever you happen to know, other than me, because I don't have a PhD, or anybody else who might know the truth about this, or do the searching yourself, do your own research. This is why I mentioned it, because it all ties together. And incidentally, random fact, my birthday is consecutive Fibonacci sequence numbers. It is 8/13. And there's only so many days of the year that are consecutive. January 1st, January 2nd, February 3rd, March 5th, May 8th, and August 13th. I'm not going to give you the year. Sorry, guys. You'll have to not know that. That's all I've got for you guys today. I really hope you've enjoyed the lecture. I don't know how many people showed up because I didn't want to look at the screen and panic in case there was a higher number than I would be comfortable with, which should be like anybody more than 1. So if you're still here and you've enjoyed this lecture, give it a like. I appreciate the likes. Give a subscription if you like this kind of content. And maybe I will consider doing live lectures in the future. If you learned anything today, please share what you learned or that you didn't previously know. Please mingle or to talk with the other commenters in a friendly manner. I want this channel to be a positive channel. I don't like arguments and things like that. So try to keep it neutral in that way or positive sounding. I will see you guys in the next video. But before I actually get there, I think I'll come over to chat. I don't know, I have to kind of kneel down because my laptop is down lower. And I will try to respond to any questions that you guys have for a few minutes that I have. Oh, one last thing to note. The Phi MC contest, I'm giving away 2 t-shirts of the Beauty of Math channel that I'm awarding to 2 of the winners as determined by the channel operators or the competition administrators. And so those are going to be given out along with 1 hour of free tutoring for 2 different individuals as well. If you want to know more about that, I'm sure someone in the comments can tell you or give you a link. I'm going to go to the chat now, which is not going to be by the whiteboard, so I can type things in there that you're asking about. Thanks, guys. I hope you enjoyed this. You can still hear me actually verbally out loud. You guys can feel free to either type questions or you can ask questions here. Cool. I thought I was going to get to like 100 viewers, but 34 is not bad. I hope it was enjoyable. Did you guys like it? Did you learn anything new? You can still hear me, right? I don't have to like type everything. Make it easier. I do play chess. I am not very good. I'm good maybe compared to people who never play because I never play, but Bry Guy right above you is really, really good, by the way. He's in my Discord server. If you want to play him, he dominates. He destroyed me. I don't mind saying that. Yeah, I hope they watch after the stream, and I hope it was helpful. Did you guys know, how many of you knew that the Fibonacci sequence was coming? Just out of curiosity. From the beginning, did you guys know where I was headed with that? I'm sure several of you did. Oh yeah, they're better than you, huh? Well, Matrices was on his chess team, I think, so. Okay, AOPS, LOL knew exactly where I was going. Good. Harshil, well, you learned some. Did I say that right? You learned something new today. I don't know how you say your first name. I know how to say your last name, but I forget how to pronounce the THUC. My real name is James, but I'm not giving the full name. Sorry, bro. Yeah, no, don't want to do that. Cool. Oh, awesome. Awesome. I like it. I wish, I saw more names like that more often. I would get better at pronouncing them. Bry Guy's birthday is a palindrome. You forgot the E, though. My age is a mystery, a super duper secret, and you don't have a high enough clearance level to know. So I'm not going to be giving that information out. Hey, Krish, good to see you. Which one would I take? Personally, I would probably always take Amy 2 if I had a choice, simply because it gives an extra week of prep time. Not for any other reason. There should be both about the same level of difficulty. The AMC B results are out for some people. I don't know how you access them. You'll have to contact your contest manager. They're supposed to have them now. I know locally several students on the West Coast have already known. Did I qualify for USAMO in high school? I did not. There was not a lot of resources when I was in high school. I only qualified for AIME. We didn't really have many different websites and books and things like that to study from. Mostly we just had past tests and access to our math teacher. It was also a small school out in the country, and they didn't really have any resources. Worst mistake I did in math. My junior year, I almost qualified for Amy. I missed by 1 because I dropped a negative sign somewhere in my calculation, or forgot 0, something like that. That's why I really relate to you guys when you make a mistake, a simple mistake. I've done it, man. I know what that feels like. I was 1 question short. Yep, just like that. How to grind? Try to manage your burnout level. Burnout is a real issue. You don't want that to happen. Try to get 1 to 1.5 hours a day, but when you need breaks, take them. I did qualify for Amy my senior year, Harshil. So even though it was sad my junior year, I used that as motivation to get to qualifying for AIME my senior year. I was the first person in the history of my high school to ever qualify. Nobody had ever done it up to that point. Yeah, I'm going to continue this stream. For about 5 more minutes. I do own dogs, and I put them in the garage early on thinking that they would be quieter, but they're actually barking like crazy. I hope you guys didn't hear it during the feed, and I want to make sure they're okay and all that kind of stuff. Any questions you guys have? Anything you want to ask about? Also, if you're interested in getting a Beauty of Math t-shirt to support the channel, you can find the video on my channel. Just look up, t-shirt or something in my channel search. Do I have kids? I do not currently have kids. Good, Bob. I'm glad you don't hear the dogs. Do they qualify for Amy? How did I do on Amy? I don't want to talk about that. No, I had just gotten there my senior year, and I didn't know what. It's actually The Beauty of Math, Rahul. TheBeautyofMath13 @gmail.com. I'll type it. I do tutoring as well, and you are welcome to send me an email inquiring about tutoring and things like that. I do have classes coming up, a website being built, all of that will happen. Would I say it was the hardest one ever? I can't say that. Yeah, that's too strong. It was definitely up there. Any advice to not fail AIME? If it's your first time taking it, I probably wouldn't worry unless you're over 130. Then you have a 130 on the AMC 10 or 12, because then you would have a legit shot at getting to the third round. If you don't really have that legit shot, don't panic. Just enjoy the process. The main thing would be, if let's say you answered 12 questions only on the AIME, it's a 3-hour test. You would have 15 minutes per question. Yeah, first time, no chance to qualify. Don't stress in the least. I would try to get 6 right. Okay, 123 is good. Yeah, you would have to get 12 right probably to qualify for the next round AOPS, LOL. Worst mistake I made in math. Like I said, I don't remember. Yeah. I dropped negatives all the time. I, forgot 0 or something like that. Yeah. Yeah, don't get a 0. That would be bad. Yeah, why are people so smart? I ask that all the time. There's several people in this chat who are actually going to be well beyond my level by the time they graduate high school. Which message, Rahul? I didn't see it. I don't suggest you get motivated to do math every day. You don't want it to become a chore, right? It should be that you want to do it. But there's going to be times, especially as you grow older, you're going to grow in interest and have more things that you want to do. And it's difficult to manage that motivation. You might have sports you want to do, or chess, or debate team, or science Olympiad. And so sometimes you might not want to. And I think that's okay. I don't think you should force yourself. I think it should be something that you have fun with. Did I do math counts? I didn't know what competition math was in middle school, so I didn't start until my freshman year. Yeah, I don't remember, Rahul, what my biggest silly was. Chores are not fun. Yeah, that's why you don't want to make math a chore. Yeah, let's win that contest, right? Free t-shirt. Yes, I do have a problem with procrastinating. As with most good procrastinators, I called myself the not very creative or unique name, the master procrastinator. And I'm sure you'll probably consider yourself that in the future as well. It's not a good habit. In fact, talk to your parents about it. I would talk to external people. Some ways to manage procrastination is to make an accountability group, right? Make a study group that you have to meet with. I would recommend where you cannot interact that much. Don't be talking all the time. Otherwise, study groups turn into social sessions, and then it's a waste of time. But you could meet online on your Zoom accounts or something, not talk, microphones off, and just work on problems at the same time. But if you're meeting someone else to do something, you're more likely to get it done. Myomotor, I would watch my how to prepare for the AMC 10 video for that answer. Too hard to explain in short. Any tips on combinatorics? I would really just, practice as much as possible. Try to find as many problems. I definitely thought the intro to counting and probability from AOPS really improved my ability. I also highly recommend you get someone to tutor. Where did I learn about contest math? My high school math teacher introduced me to it the spring of my freshman year. Favorite area of math? I actually think the geometry proofs were my favorite, for reasons I'm not going to fully explain right now. The modern proofs that you guys do aren't that great. There was a lot of really great ones in the past, and the logic behind it was enjoyable. You can see 2 videos on my channel where I go into 2-column geometric proofs, which is not the way the majority of the world does them, but locally in America, they are used that way. You can see me explain on that video why I like geometric proofs, or in the video, why do competition math, or what is mathematics. I'm probably going to refilm those videos in the future because they were filmed on older software, camera and sound system. And so, yeah. I don't have any advice for math count state prep. Just practice problems is all I will say. Thousands and thousands of problems. I missed a question up here. What do you recommend for someone in 8th grade AMC 10 first time? That's a really good score, Rahul. I would honestly, again, watch the How to Prepare for AMC 10. I can't get into specifics right now because I would have to think about it, but we could always meet for a consultation if you want to email me. Right. Force everyone. You guys can join Discord if you want. Please understand it's in development and I'm not always there. Matrices runs it. He's doing the best he can and he's a great help and he's a good dude. So he's got his own channel, Explore Math. Be sure to give him a subscribe. JMO cutoff, I don't know. I would say like at least 230, maybe 240. We'll see. Senioritis, yes, that's difficult to deal with for sure. I remember senioritis. Guys, I'm going to have to get going here in a minute because I do have to teach a class soon. I wanted to thank you all for coming. I'm sorry if there's other questions I didn't have. Feel free to leave them in the comments. The live chat is about to end. You can carry on the discussion after the comments are there. Thanks so much, guys, for joining, and I hope you have a great rest of your day. Good luck in your contests. I'll go from up above, I guess, and say goodbye this way. All right. Oh, my microphone came off, so I'm down here. Bye, guys. Have a good day. I will see you in the next video.